Hi, this lecture is it's me trying to help you understand what you can do with the Heisenberg uncertainty principle. So on the one hand, there is, say, understanding why there is an uncertainty principle, right? The uncertainty principle is a fundamental physics law, right? So understanding the uncertainty principle and where it comes from is on the one hand, one important thing, but there's another important thing, that is, how can you use it to make predictions? Like, how can you use it to do physics? And so what I'm going to discuss is a little bit of both of those things. Like, where does the Heisenberg uncertainty principle come from? And then how can you approximately use it, right? So I'm going to sort of abbreviate the Heisenberg uncertainty principle as the HUP, Heisenberg Uncertainty Principle, right? And it is a statistical, actually I need to spell that correctly, statistical law. So for example, you're getting used to thinking about, I'm going to actually ignore time for a little bit. Let's think of one-dimensional wave functions, right? So I've got this psi of x. You have seen that psi star psi is probability density, right? So that's one thing. So probability and the Heisenberg uncertainty principle is statistics, and probability and statistics have a lot to do with each other. So psi star psi being a probability density is important. So you've seen Heisenberg's uncertainty principle probably written this way. It's delta x times delta p is bigger than or equal to h bar over 2. So what the heck is this in statistics, and what the heck is this in statistics? Like, we can't just say, oh, it's the uncertainty. We have to actually define what's meant by delta x. Like, how would you get delta x from some more fundamental thinking, right? So the way you get it actually is this way. So define delta x to be what's called the standard deviation in measurements of x, where the standard deviation is this kind of a construction. It's so you go, you ask, what is the average value of x squared? And you ask, what's the average value of x? And then you square that afterwards. And you take the difference. So the standard deviation, it's the deviation between the average value of x, which adds up a certain way, and then you square the result afterwards. And compared against when you take x and you square it first, and then you ask, what's the average of that? So remember, the expectation value of x is the integral of psi star x psi dx. And so if you want that squared, you do the integral first and then you square it. And then the expectation value of x squared, that's the other thing, is the integral of psi star, you put x squared in between psi dx, right? So yeah, these are two different things. They are statistical measures of these two qualities, and we can say what a sigma x is, and we'll describe this as a rough description of the spread in x values, right? It's a measure of the spread in the x values. It's a measure of the spread in the experimental outcomes of experiments. So in a sense, right, like you might say, or actually, let me move on and describe delta P instead. So delta P is this thing called sigma P. And actually, let's be specific. It's the momentum in the x direction, right? And so let's be very careful. It's not the magnitude of the momentum. It's strictly the momentum only in the x direction. And simultaneously, there's a Heisenberg uncertainty principle in the y. It's the same. And the z. So etc. But the Heisenberg uncertainty principles don't exist between, say, uncertainty in location in x and uncertainty in momentum in y. There's actually no uncertainty principle there. Okay, that is, you can know the x location and the y momentum to whatever precision you want, is the idea. So here, so the uncertainty in the x direction momentum is similar idea. You take p sub x, you ask what's the average value of the square of it, and you subtract off inside of the square root. You take the average value of p sub x, and then you square it afterwards. That's all inside the square root, right? And you can remember that the average value of p sub x, right? It was kind of strange. You had to do the integral, right? Psi star, and then you had to do minus IH bar d by dx on psi, and then you integrate dx. So if you want to know this thing squared, you have to do all this squared, and p sub x has an average value. I just did that, sorry. Okay, so this one is a little bit more difficult, but or it's just takes a little bit more writing. So you're going to do the integral of psi star, and then it's actually h bar squared with a minus sign, and then d squared by dx squared on psi, and then you integrate that. So you have to take a double derivative of psi on the inside, and then afterwards multiply by minus h bar squared, and then multiply by psi star. So you got this function of x on the inside of the integral that you have to integrate over all the possible x position values you can imagine. All right, so you get this. So you can imagine that the precise value, right? So the value of sigma x, sigma p sub x depends on psi. It depends on the wave function itself, right? Because you look at, you see when I define this thing, the wave function's everywhere in this really complicated way, right? And then even after you find each of these different things, you have to put them together in this other thing. So it's heavily dependent on the shape of psi, is the idea, right? So for any particular psi, whenever you do this, it's only ever something similar to h bar. Like the precise value is going to be, it's going to be some factor times h bar. The factor could be 100, it could be 10 to the fifth, it could be, it could be 1/2, right? The point is, though, is depending on the wave function, you're going to have different values that multiply the h bar. So this particular case of delta x delta p being equal to h bar is for a special psi, and this special psi is referred to as a Gaussian. It's got a particular locality. In a sense, it kind of like minimizes the localities simultaneously. So it minimizes, it's sort of like, maximizes localities simultaneously in these two variables, the spread in position and the spread in momentums. And it does it in a very special way. Oops, and I forgot, it's divide by 2. So this turns out to be the minimum possible. So over all possible psi shapes. Okay, if you stay in math and you study, for example, Fourier analysis, you might prove this one day. Yeah, but for us, I'm just going to say that it's the case. Yeah, you can look around on the internet if you want to learn more about this. But anyways, you can see that the Heisenberg uncertainty principle is not fuzzy. That is, it's not something that's based on somebody's gut, although actually the origination of the uncertainty principle, I think, was like an amazing physics hunch. But later on, people figured out, right, physicists and mathematicians figured out how to make it derivable. You can derive the uncertainty principle from more basic fundamental ideas. And that's what I've showed you here with all these integrals and these standard deviations, right? Okay, so this is all well and good. The reason I wanted to show you all of this stuff is to say that since delta x delta p has a value that depends on psi, let's just approximate with delta x delta p is something like h bar. And so that's why I called this lecture Estimate with Heisenberg Uncertainty Principle, right? So here's an example. Electron confined to atom, right? So here is an atom, and the electron is in here somewhere, is the idea, right? So the electron is somewhere in here. And so notice that we really want to think in terms of estimations. So let me show you how that might go, right? So this is an important ability of a physicist and an engineer, is to make estimations that are calculated. These are often referred to as back of the envelope calculations. Famously, this comes from, say, a bunch of physicists at a bar, and the only piece of paper that they have around, they want to describe something to each other, is an envelope. So they take the envelope out of their pocket, they take their pencil, they flip the envelope over so that they can write on the back side where it's clear, and you only have this really, really small amount of space to calculate something. So instead of keeping track of a lot of detail, you just keep track of estimated details. And sometimes all you want to keep track of are the factors of 10, right? Is the answer 10 to the 4th? Is the answer 10 to the 30th? Is the answer 10 to the minus 27, right? Those are all extremely different answers. And just knowing that it's 10 to the minus 27 and not 10 to the minus 25, right, is a lot of information, and you can make that judgment call just paying attention to factors of 10. And so, in a sense, that's all we can keep track of with this sort of estimation scheme with the Heisenberg uncertainty principle. So an atom it tends to be thought of as being an angstrom wide. Let me rewrite that. So there's this special unit symbol called the angstrom. And 1 angstrom is the same thing as 10 to the minus 10 meters, or 0.1 nanometers. And people typically think of atoms as having a size on the scale of an angstrom. So we will say that that is where the electron is confined to. That's the localization, or the uncertainty in the location of our particle. So the uncertainty in the location is something like 10 to the minus 10 meters, right? Which is the same thing as 0.1 nanometers. And so this I arrived at not because I know psi, right? If I knew psi, then I could go through all this stuff that I showed you and be able to actually calculate an uncertainty. But I do not know psi, so I'm going to just approximate with Heisenberg's uncertainty principle. So I'm going to say, estimate, back of the envelope style. And what I can say from that, though, is that means that delta P is something similar to h bar over 0.1 nanometers. So that's pretty cool. So, but what am I going to get from this, right? What does delta P mean? We could say that it roughly represents the magnitude of the momentum. So if I wanted, I could get the magnitude of the momentum from this. So delta P is something like, if I could imagine that the electron has a momentum, I could imagine, it's got a magnitude of momentum. And I can say what the electron's momentum is. So what you'd have to do is put in a value for h bar, right, which is a fundamental constant of nature. It's not hard to look up. And then divide out this distance. And the idea is you'll get an estimate for the magnitude of momentum. What this can also be used to do, but this is a little bit more of a stretch, or actually it's not quite a stretch yet, but you can give an estimate for the kinetic energy. You just take the estimate for the magnitude of the momentum, right? You square it, divide by 2m. So we're identifying this as being something similar to this expression, and delta P is h bar over 0.1 nanometers. So you could say that the kinetic energy is approximated now, right? So let's be careful. It's not equal, but it's something similar to h bar over the confinement squared, and then 1 over twice the mass of the electron. This right here can be argued to be something similar to atom energy transitions. That is, these are the energies of the photons that come away, but only estimates, right? So you can begin to estimate how much energy the photon comes away with when the transitions are of the scale of the kinetic energy. So this is all to say that using Heisenberg's uncertainty principle to do physics with it, to sort of leverage the ideas, is really an estimation process. So the answers you get from using it this way are estimates, and estimates are only good to roughly the factor of 10. So there's this other one though that shows up in books. It's so this is another example, and it's an example of a strange uncertainty principle that's written this way. And I say that it's strange because the derivation of this is really, really different than the derivation of that I showed you up here, where you have all the wave functions and stuff. You can read about the fact that this is a very different kind of uncertainty principle, but I'm going to show you a use case. So an example use case. All right. The idea is when you have an atom, so here's an atom, right? It's going to transition, so its electron orbital, let's say, transitions from some high value down to some low value. So the electron actually moves down in orbital, so the energy, internal energy of the atom gets smaller, but because of the conservation of energy, that energy needs to go somewhere. And the Bohr model and the sort of the quantum mechanical way of thinking about it is that lost energy is the energy of a photon that travels outwards. But here's a really interesting question. How much time does the atom live in the excited state, right? And this lifetime is a statistical quantity, right? Often, lifetimes of things are referred to in the half-life sense. You may have heard this term before. So half-life is a statement not about how much time it takes for any particular transition to occur, but it's the time it takes for a really, really large population of atoms, such that half of those atoms, by the time that this amount of time has gone by, half of them have lost their excited states. Half of them have emitted a photon. So some of those atoms are going to emit photons in the beginning of the half-life. Some of them are going to emit photons towards the middle of the half-life, and some are going to emit photons towards the end of the half-life. And delta T, you might say, is something like the half-life. And atomic transitions have half-life times of something like 10 to the minus 8 seconds. So half-life is a scale of a lifetime. You might imagine that there's some sense in which the average atom decays in some amount of time, similar to T half-life, right? Similar to 10 to the minus 8 seconds. Yeah. So what does this say, though? What's interesting about this is that if the photon comes, let's say that the photon's transition is about 10 to the 14 hertz. This might be a visible wavelength photon, right? The delta E aspect, right, of the Heisenberg uncertainty principle, it's related, or it's roughly approximated to be h bar divided by this time. So right now I'm estimating something with the Heisenberg uncertainty principle, but let's figure out what I'm estimating. So if you go through, you're going to get a spread in energies. And this can be associated with a spread in frequencies. And that's a spread in frequencies for these photons. That is, we're not just going to emit one frequency of photon, we're going to emit photons that all have roughly this frequency, but there's going to be a spread in the emitted photons. That is, they're not all going to be exactly the same color. They're going to have some variation in their color. So E equals HF. So this is a quantum statement. If you have a photon of this frequency, that photon carries this energy, right? And so it goes sort of along the same lines. If I have a uncertainty or spread in the energy, I've got an associated spread in the frequency. And this is what I mean by this delta F. So if you look really close at the atomic spectra, right? So you've got some gas of these atoms, and somehow you let light, so you imagine just paying attention to some of the light coming off of here. If you send it through a prism, right? Let me be more careful about this drawing. So a prism is this kind of wedge of glass or crystal, and the light is going to take it's going to take a refracted path through the prism, right? And if there are multiple frequencies in this light, they're going to go to different angles. And that's how you can look at the spectrum. The spectrum comes through at different angles through the spectrometer. This is the spectrometer, right? And if you look really close at the light coming in this direction, this light might be the 10 to the 14th hertz light that I'm saying is what's being emitted because of this particular transition that has a half-life of about 10 to the minus 8 seconds. But what Heisenberg's uncertainty principle is saying is that frequency has a little bit of uncertainty. So if you're just looking at this light that's showing up at this angle around this particular color that's coming away, like this could be red or something. This red color is not a single frequency at 10 to the 14th hertz. So if this is the frequency axis, and this is the brightness or the intensity, what Heisenberg's uncertainty principle is saying is that actually what comes away is lots of frequencies of light that are all really similar to 10 to the 14th, but that have a width of about 10 to the 8th. I think when you calculate it in these numbers, it's about 10 to the 7th hertz. So this is a broadening of spectral lines because of Heisenberg uncertainty principle.